Hello everyone, and welcome back. Today we're going to continue our exploration of linear relations and functions and focus on some basic applications that linear relations can immediately give us just from the basic things of linear relations that we've discussed so far. So let us consider the first example. Suppose that your business starts with $500 and generates $34 in passive revenue per hour. How much money will your business have in 2 days or 48 hours? If you want to try this problem on your own, you may want to pause this video and give it a go. Otherwise, let's get right into the solution. So the first thing that I want to do is first clarify the domain of my function. So I'm going to be using t to correspond to my domain since we're looking at revenue over time. So t is equal to 0 is going to correspond to now. So now my current revenue is going to be equal to $500. So when t is equal to 0, r of t is going to be equal to 500. And let's assume capital R represents the revenue in terms of US dollars. And how much money will we have in 2 days? So since this is in the unit of hours, t is equal to 48 must also be in hours as well. You cannot use 2 unless you correspond to that to days, but then you have to convert otherwise, right? Because we know how things are changing per hour, so you would have to change this 34 per hour into something per day if you want to keep things in 2 days. So that's very important to know. But if we're going to be working in hours, then everything is going to be perfectly fine. So we want to find the value of r when t is equal to 48, right? So based upon the information that we know that 0 comma 500 belongs to our revenue relation. So that means when we're looking for our constants a/t plus b, we know that this corresponds to the y-intercept, which will help us get the value of b. That means the y-intercept for our revenue relation is going to be equal to 500. Therefore, the only thing that we need to figure out is what is the slope of our revenue relation. So let's think about this for a moment. So when t is equal to 1, i.e. after 1 hour, how much money will we have? Well, we will have the amount of money that we had before plus the amount of revenue that we generate per hour, which is going to be equal to 34. Therefore, this is going to be equal to 534. So that means what? That means 534 is going to belong to our revenue relation as well. That means since we have 2 points, 0, 500 and 534, we have that the slope of this linear relation is going to be equal to r1 minus r0 all over 1 minus 0. So that's generally y2 minus y1 over x2 minus x1, where x is time and y is revenue. So that's going to be equal to what? So that's going to be equal to, let's actually write t1 minus t0 just to be a little bit more clear there. So that's going to be equal to 534 minus 500 divided by 1 minus 0, which is going to be 34 divided by 1, which is equal to 34. So once we have that, that gives us our revenue relation. So that means our revenue relation, R of t, is going to be equal to 34t plus 500. So once we have our revenue relation, we can actually evaluate this at practically any time along our time domain that we want, but of interest to us is 48 hours, which is 2 days. So how much revenue will we have after 48 days? So that's going to be equal to 34 times 48 plus 500, which is going to be equal to 1632 plus 500, which is going to come out to $2,132. That's how much money our business will have after 48 hours, or equivalently how much money we will have after 2 days. Consider the next example. Suppose that the average of gas prices increases linearly over time. Assume firstly that the gas price in the year 2000 was $1.51, and in the year 2010 the average was $2.96. How much will the average gas price be in 2035 if it continues to follow this linear trend? So the first thing that we need to do, just like the last problem, is to start off by defining what our domain variable is. So what we're going to begin by doing is we're going to let t to be equal to 0 correspond to the year 2000, and let's assume that if we consider, for example, t is equal to 1, that would be 1 year after t is equal to 0, which would be 2000, which would be the year 2001. So let's assume that t is going to be measured in years. So when t is equal to 0, what is the average gas price? So if t is equal to 0, let's assume that our output variable, which is going to be the gas price, is going to be in the units of dollars as well. So let's assume that that y value is going to be 151. So the next piece of information that we're given is the year 2010. So if we're using years as our unit of time, that means this is 10 years in difference. Therefore, t is equal to 10 is going to correspond to the year 2010. That means the associated point for our model is going to be 10 comma the average gas price in that particular year, which is given to be 2.96. So now we have 2 points, therefore we should be able to construct our price model, in particular P of t is equal to AT plus B, where A and B are some parameters for which we seek to find. So just like before, we already know that 1.51 is going to be our vertical intercept, and then we just need to figure out what our particular slope is going to be. So the slope of the line that passes through these 2 points is going to be equal to what? So it's going to be equal to y2 minus y1 all over x2 minus x1, which is going to be equal to 1.45 divided by 10, which is going to be equal to 0.145. So if you sort of want to think about what this 0.145 means, it just means that on average gas is increasing at about 15 cents per year. So if we want to now construct our model, that means the price of gasoline as a function of time is going to be equal to 0.145 of t plus 1.51, where t is measured in the number of years since the year 2000. So since we're interested in the year 2035, this is going to correspond to the year 35. So we just need to evaluate this function at 35, and that's going to give us the information for which we seek. So therefore, P of 35 is going to be equal to 0.145 times 35 plus 1.51, which is going to come out to 6.585, so about $6.59 per gallon as an average in the year 2035. Now, there are several other questions you could ask with the same exact information. For example, one could ask, when was the price $0 per gallon on average? Right? And technically somebody could pay you to take something. Technically, from the economics point of view, that's definitely a possible thing. But according to this model, then we should know, since the line is obviously increasing, then there is a point in time for which the gas was negative infinity dollars on average for gasoline, according to this model. So what we can do is we can find the time t such that p of t is equal to 0. That is, we seek to solve the equation 0 is equal to 0.145 times t plus 1.51. So if we solve this equation for t, we can easily get that t is going to be equal to negative 1.51 divided by 0.145, which is approximately equal to negative 10.41. And keep in mind, this unit is in years. So how do we interpret that negative number? So this is about 10.41 years before the year 2000, which would be about the middle of the year of when. When do you think it is? You should be saying 1980. 189. But those are some of the questions that you could answer in regards to this average price model for which we have constructed based upon the information that was given. Now let us consider the third example. Suppose you are standing in the xy plane at the point 5, 3, and someone else is to stand on the line x is equal to 10. If the units of distance in this plane is in meters, what is or what are the points x, y for which a person needs to stand in order for that other person to be 25 meters away from you? Every time you have a geometry problem, at least for me, sometimes it's best to start with a picture. So we are practically hanging out in the positive spectrum of the plane, so technically I only need to focus on the right half of the plane. So where are we standing? We're standing at the point 5, 3. So if we just give a quick sketch of where we are, we're located right here. Let's call that person 1. The other person needs to stand along the line x is equal to 10, which is located somewhere along here. So obviously, if we were to project horizontally, the distance from 5 to 10 is going to be equal to 5, but we need that person to be 25 meters away from us. Therefore, it needs to be either further up or further down the line. Therefore, we need to find the point or points such that the distance between person 1 and person 2 is equal to 25. And you should be able to at least intuitively see that there should be another point down here somewhere as well for which that person could stand and still satisfy the given requirements, i.e. we need to find the point P2 that satisfies the equation. The distance from P1 to P2 is equal to 25 meters. So we already know the distance equation between 2 points, and we actually already know what one point is. We just need to figure out the other point. But we do know that the x-coordinate of the second point is going to be 10 comma something, right? So we know it's going to be 10 comma something, so we just need to figure out what that y value is equal to. So we know that the distance must be equal to the square root of x2 minus x1, so it's going to be 10 minus 5, the quantity squared, plus y2 minus y1, and we know the y value of 0.1 is going to be equal to 3, the quantity squared. So what I'm going to do is I'm going to get rid of the square root by squaring both sides of this equation. So I have 25 squared is equal to, so 25 squared is equal to, then we have 10 minus 5, which is going to be 5 squared, and then plus y minus 3 squared, so y minus 3, the quantity squared, and then we just need to solve this equation for y. So we should be able to find that 25 squared is going to be equal to 625. So we have 625 is equal to this right-hand side. So we have 625 is equal to 25 plus y minus 3 squared. Now you could expand this out, but later when we focus on quadratic relations and quadratic equations, you will eventually see that if we only have one instance of the variable y, it's actually better if you just keep it inside of the parentheses and just remove that square that's sort of trapping it inside of those parentheses. So I'm going to begin by subtracting both sides of this equation by 25, and then we're just going to be left with y minus 3, the quantity squared, is equal to 600. So once I have that, then I'm going to take the square root of both sides of this equation. So I'm going to have the absolute value of y minus 3 is going to be equal to the square root of 600. And then in order to remove the absolute value, keep in mind absolute value, the inside could have been positive or negative root 600 for this equation to be satisfied. So I'm going to have y minus 3 is going to be equal to the square root of 600, or y minus 3 could have been equal to the opposite of minus 600, and then I can just add 3 to both sides of both of these equations, and I'm going to have y is equal to 3 plus the square root of 600 as my first possible y value, so that's the one that was above. Or y could be equal to 3 minus the square root of 600. Since we're working in practical geometric manners, you should be able to give at least an approximation to get some idea of the y value's value. So if we want to approximate this as a decimal, you're going to have 3 plus the square root of 600 coming out to be approximately equal to 27.49. or the y value for that second person could be approximately equal to negative 21.49. So the values that they could stand is either going to be 10 comma 27.49 or 10 comma negative 21.49, and they will be 25 meters from where you're standing, which is the point 5 comma 3. Now let us consider this revenue, profit, and cost example. Suppose that you sell X donuts at $1.30 per donut, and let us assume that it costs 15 cents to make each donut. Let us also assume that there is a daily cost of $850 per day due to labor, i.e. to pay the people that are working at this bakery. How many donuts should you sell each day in order to break even? So here we're assuming that we're only selling one item at this bakery, and that is donuts. Later on, when we consider multivariable functions, you could of course extend this problem to the general case, but let's keep this to a single variable function, in particular a function of the amount of donuts that we sell. So the first thing that we need to construct is our revenue function. So if I tell you how many donuts that we sell, you should be able to tell us how much money we will make from those donuts. So the revenue function obviously is going to be a linear relation. In particular, if I sell 0 donuts, we make $0. If we sell 1 donut, we will make $1.30. If I sell 2 donuts, then I'm going to make $2.60, i.e. 2 times 130. And you should be able to see that this is just going to be equal to 1.30 times x, and you should be able to construct that answer even if you were to approach this from the slope and intercept perspective. Now let us look at our cost, and keep in mind this is per day. Right? So how much does it cost to make each donut? So it doesn't cost anything to make 0 donuts. It costs 15 cents to make 1. It costs 30 cents to make 2. It costs 0.15 times x donuts to make x of them. And keep in mind, per day we also have this fixed cost of $850. Once you have your revenue and cost function, which are both linear functions as we should be able to see, then we should be able to construct what we call our profit function, which is also going to be a linear function as well, which is constructed from revenue and cost, in particular revenue minus cost. So if we substitute our revenue and cost functions into this relation, we're going to have our revenue function 1.30x minus our cost function 0.15x plus 850, and be sure to put parentheses around that because this negative sign needs to distribute into that addition sign. So once we have that, then we're going to have our profit function. So we're going to have that our profit function is going to be equal to 1.30x minus 0.15x minus 850, which will simplify to, so 1.30 minus 0.15 is going to be 1.15x minus 850, and that is our profit function as a function of the number of donuts for which we sell. So what we need to figure out is the value x for which leads us to break even. And if you don't know what break even means, this is the point for which our profit is equal to 0. And hopefully, since this is a linear function with a positive slope, after this point we will have a positive profit for each donut for which we sell. And for each donut that we sell less than this magic little number, then we're going to have a loss, in particular a negative profit. So let's solve that equation and see what we will get out of the end. So we're going to have 0 is equal to 1.15 times our break-even unit x minus 850. And then if we add 850 to both sides and divide by 1.15, we're going to have x is equal to 850 divided by 1.15. So once we actually work that out, that's going to come out to approximately 739.13 donuts. And let's assume for practicality purposes that you cannot sell a fraction of a donut. So therefore we can only sell 739 or 740. But if you notice, 739 is not enough because our profit will be negative at any point to the left of 739.13. And therefore 740 is our magic number, and this is enough to break even. But of course, 740 is not exactly equal to zero profit. Therefore, we will have a little profit left over, which is always not a bad thing. The last application that we're actually going to look at for linear relations actually is an application to give us some sense of increasing, decreasing, or constant behavior for functions or relations that are not necessarily linear. For example, let us assume that we have this graph of this function f shown in gray in this little sketch. As we can see, this function does have its ups and downs, but is on average increasing, decreasing, or constant on some particular intervals. For example, if we look at this little green portion here, that function is practically increasing on that little region. And if we sort of look at this almost shallow region here, it is slightly decreasing, approximately constant, depending on that particular sketch that I have drawn here. But it's definitely decreasing on that interval, although subtly, and then it's going to be definitely be increasing on that right interval in pink for which I've sketched there as well. So for example, if I were to pick any particular 2 points on here, for example, this point and that point, and I were to connect them with a line, then obviously this line is greater than 0. So what have I actually done here? Well, I've chosen a x value a and another value x value over here, let's call that b, and of course that's associated to some y value f of a, and that's going to be associated to some y value, say f of b. So I should be able to find the slope of the line that passes through those 2 points. And then, of course, we would be able to tell whether it's positive, negative, or 0. And that will tell us, on average, that the function is increasing, decreasing on constant on that interval a, b for which we have chosen. So if we sort of write that in a equation format, so the slope of the line that we're going to be interested in is going to be called the average rate of change of the function on that interval, which we're going to note as a for average rate of change, subscript f of the function for which we're finding the average rate of change of, and then also parentheses ab of the interval for which we are finding the average rate of change of the function f over. And from this little picture we have 2 points, a f of a and b f of b. So this is going to be equal to y2 minus y1 over x2 minus x1. And this equation is going to be very, very important, especially for those of you who are going to extend your foundations of math skills into instantaneous mathematics or calculus 1, which most people call it. So let's actually look at a particular example, and let's sort of use this average rate of change format to see if this function is, for the most part, increasing, decreasing, or constant on some particular interval. So let's assume that we have, for example, a profit function that is nonlinear. So you can consider this, for example, a donut profit function. So x is the number of donuts we sell, for example, in thousands. And let's assume that this profit function is given by x cubed minus 2x squared plus 1, with the domain restriction that the domain of p is going to be equal to 0 to infinity. So one could of course plug in a bunch of points into this function and get some graph out, but you should be able to see obviously that the y-intercept is going to be equal to 1. If you plug in a bunch of numbers, you will be able to see that it sort of has this behavior here. In particular, this value is exactly 1, and this value here is approximately, but not equal to exactly, 1.6. So it definitely does have a decreasing pattern from 0 all the way to some value in between 1 and 1.6. And then it does have an increasing pattern after that local minimum up to positive infinity. So let's assume that we want to find the average rate of change of our profit function p on the interval 1/2 to 5/2, or in decimal form, the average rate of change of p on the interval 0.5 to 2.5. So where is 2.5? Well, 2.5 is going to generate some point all the way up there, and 0.5 is going to be located right here. So if this sketch is actually correct and we were to draw a line through these points, then we would see that the profit function is on average increasing on the interval zero point 0.5 to zero point 0.5. So let's actually plug these points in and see what that is, because this graph could be wrong or heavily misleading. So this is going to be equal to the profit function evaluated at 0 0.5 minus, actually it should be the upper bound, so 2.5, y2 minus y1, all over x2 minus x1. Of course, you can reverse the order if you want. You could do f of a minus f of b over a minus b, but as long as those domain points and those range points match up in the same column, you should have no issues. So once you plug in 2.5 into this function and do all that fun little decimal math, or fraction math if you prefer, that's going to come out to 4.125 minus, and then when you plug in 0 0.5, that's going to come out to 0.625, all over 2.5 minus 0 0.5, that's obviously going to be equal to 2, and that's going to come out to 3.5 divided by 2, which is going to be equal to 1.75, which is obviously greater than 0. So from this number, what can we say about our profit function? That means, on average, our profit function P was, actually let's interpret this 1.75 a little bit more accurately. So on average, our profits was $1.75 per unit sold, or per 1,000 units sold if, for example, this is in thousands of units of X. But if this is, for example, thousands of units, that's 1.75 on average profit per 1,000 units sold when we are selling between 0 0.5 and 2.5 units, or between 500 and 2,500 units if you're considering this to be in terms of thousands, right? So that would be 5,000 units or 2,500 units if this were truly in thousands of units, which I didn't specify, so that's pretty much open-ended depending on how you've defined these particular units. But these applications are not, of course, not the only applications that you can use linear relations for, but they are some of the basics, and especially this average rate of change formulaing concept is definitely going to be very, very useful later on. So I hope you enjoyed, and I'll see you in the next video. Take care.